Okay, so now we've done speed, now we've done velocity. The next thing we are going to tackle is acceleration. Now acceleration actually is based upon both of them if they are going in just one direction, if it's a linear motion. So we can use the same formula for either one. Otherwise you're going to have to do distance and displacement like we did for speed and velocity. But generally we don't use displacement much for acceleration, except in circular motion, and that's just a long way down the road. So acceleration is defined as the change of velocity compared with the change of time. And the formula for that is delta V over delta T, which is what we can also express as this. A equals delta V over delta T. And remember, delta means change. So that's VF minus VI over TF minus Ti, where F means final and I means initial or beginning. You use initial a lot because you're going to see it a lot in the book, but it means beginning. And for T sub I is almost always, but not completely always equal to 0. Usually starting at some point at your beginning, and if you're not measuring the time up to that point, then that is technically, in relative terms, a 0. But we'll talk about what happens if that's not the case. So and I've got it written here too with parentheses. When you put it into the calculator, that really is how you should put it. But you won't see the formulas in books written with parentheses. The SI unit for acceleration is meters per second, because what you're measuring is the change of velocity with time. And the change of velocity, or just the velocity in general, is meters per second. And if you're comparing that to time, that's going to be meters per second over seconds. And when that happens, you have two denominators, you're going to multiply together, and that's going to give you what we more commonly use as meter per second squared for our measurement of acceleration. Let's take an example. A car travels on an interstate and hits a construction area. For 10 miles, the car travels at a velocity of 45 miles per hour during that trip in the construction area. After a while, the construction area is gone and the car accelerates up to 65 miles per hour in half a minute. What is the acceleration in meters per second per second? Okay? Now, the problem with this is that we have miles per hour, but we know that we want meters per second squared. So everything's got to be in terms of meters and seconds and not miles and not for hours. So we have to convert everything over right away. So what I did here is I subtracted 65 minus 45 miles per hour, and the change in velocity is 20 miles per hour. Now I would suggest is the best time to convert it before you actually divide it by the time, which of course is going to be 30 seconds, half a minute. So the conversion here is 20 miles per hour times, and then the conversion here, we want to cancel out the miles on the top, so we have to put the 0.621 miles on the bottom. I'm using the conversion that for every 1 kilometer is 0.621 miles. You can use whatever you can find in the book or in your internet or whatever, but if I were to give you a quiz, I'm going to give you distinct values to use. So it's all a matter of canceling correctly using the proper labels in the fractions. So anyway, so I'm using 0.621 miles as equivalent to 1 kilometer, so the miles on the bottom. Then I have to change the kilometers to meters, and that's 1,000 meters per 1 kilometer. And then I'm going to change the hours to seconds, and I'm just using the shortcut 3,600 seconds for every 1 mile. The seconds are on the bottom, and the hours are on top because the hours are on the bottom over this 20 miles per hour. And then I calculate that and round out 3 significant figures, and I'm going to get 0.298 meters per second squared. That is the measured calculation for that. Very simple mathematics, it's almost plug and play. But you need to make sure and put that formula into your physics toolbox. Delta V equals delta RA is equal to delta V over delta T. He stumbles around. Let's do another example so we get another concept of acceleration. A car comes to a stop in 5.25 seconds after traveling at a velocity of 25.0 meters per second. What is the acceleration during the stop? All right, so again, delta V is VF minus VI over TF minus TI. So we plug in the numbers. We know that at the beginning, you're traveling 25 meters per second. So that is your initial velocity, that goes right there. If you are stopping, that means you are not moving anymore, so that's 0 for your final velocity, that's going to go right there. Your initial time, of course, is 0 when you start hitting the brakes, it's 0, so that's your, it's 0 when you start, right, so that's the initial, and then the final, it took 5.25 seconds to get to that point. If you put the parentheses in there, round off 3 sig figs, you get negative 4.76 meters per second squared. That really is all there is to that. So, the question we have to look at each other is, what the heck does that negative sign mean? Why did we get it in the first place? Well, you know that you're not speeding up, you're slowing down. So if we are establishing a positive value as being an increase in acceleration, then a negative value is a decrease in acceleration, or an increase in velocity versus a decrease in velocity. So we have a special term for that, and that term is deceleration, or decelerating. So deceleration is negative acceleration. It's calculated exactly the same way, but you are going to end up with a negative value. Your practice problems related to this in your textbook, page 61, problem 24, 26B, and 30. And again, if you have questions, let's talk about them in class. All right?